Combination and permutation. Distinguishable permutations and other examples. What are they? Combination determines the number of possible arrangements where order does not matter. Permutation determines the number of possible arrangements where order matters. Why? Helps to crack codes, especially when you forget a password. Interesting fact: a group of rhinoceros is called a herd or a crash. Who knew? The plural of rhinoceros is rhinoceros. Or it could be rhinoceroses. I didn't. Now, let's take a look at some theorems. The first theorem on distinguishable permutations is if R objects in a collection of N objects are alike, and if the remaining objects are different from each other and from the R objects, then the number of distinguishable permutations of the N objects is N factorial over R factorial. And the second theorem on distinguishable permutations is if in a collection of N objects, N sub 1 are alike of one kind, N sub 2 are alike of another kind, N sub k are alike of a further kind, and N is equal to N sub 1 plus N sub 2 plus plus N sub k, then the number of distinguishable permutations of the N objects is N factorial all over N sub 1 factorial times N sub 2 factorial times N sub k factorial. Now, let's find out what these mean by putting these theorems into action. Let's take a closer look at the examples we're going to discuss in today's video. Let's take a closer look at example 1. Now, let's read the steps. Step 1. What is N? The object. Step 2. What is R? The position. Step 3. Use the formula. Step 4. Follow order of operations. Now, let's read the question. Find the number of distinguishable permutations in the word Tennessee. First, let's write down the word so we can show our work. Now, let's write down how many letters are in the word Tennessee. So we have 9 letters. Now, let's take a closer look at the letter E. How many E's do we think we have? That is correct, 4. They're in the 2nd, 5th, 8th, and 9th positions. What happens if we switch the 8th and 9th E's? Nothing happens. We still have the word Tennessee. And we can keep switching the E's around and still have the word Tennessee. Let's do it a few more times. We could have the 8th E written in the 5th position, then the 5th E in the 8th position, then the 9th E in the last position. Or we could switch the 9th and 5th E's around. Next, we could have the 9th E in the 5th position, then the 5th E in the 8th position, then the 8th E in the last position. Or we could switch the 8th and 5th E's around. Now, how many different permutations do we have with just the letter E? That is correct, 24, or 4 factorial, because 4 times 3 times 2 times 1 is 24. Let's put the numbers back in order. So we have to do that with each letter. So let's count how many T's, E's, N's, and S's we have. So we have 1 T, 4 E's, 2 N's, and 2 S's. So to find the number of distinguishable permutations in the word Tennessee, we put the total amount of letters the word has on top, which is 9, and we divide it by the amount each letter has. So 1 for T, 4 for E, 2 for N, and 2 for S. Make sure to put a factorial after each number. Now, we don't need to put 1 factorial for T, since 1 factorial is 1, but that's okay, let's put it anyway. And that follows the formula, N factorial all over N sub 1 factorial times N sub 2 factorial times N sub k factorial. And if you put it into the calculator or simplify, the result is 3,780. That is example 1. Let's move on to example 2. Now, let's read the question. In 5-card poker with a standard 52-card deck, remember, there are 13 in each suit and 4 of each kind. A. How many hands are possible? B. How many full houses are possible? Remember, a full house is 3 of one kind and 2 of another kind. Let's start with A. How many hands are there? One hand could be the ace of diamonds, the 2 of spades, the 3 of diamonds, the 4 of clubs, and the 5 of hearts. Or we could have the 5 of hearts, the ace of diamonds, the 2 of spades, the 3 of diamonds, and the 4 of clubs. Or we could have the 4 of clubs, the 5 of hearts, the ace of diamonds, the 2 of spades, and the 3 of diamonds. What do we notice about each of these hands? That is correct. The three different hands are actually the same, so order does not matter. That means we're going to use combination to find our answer. In this case, N is 52, since there are 52 cards in a deck, and R is 5, since each hand has 5 cards. Let's substitute 52 for each N and 5 for each R. So now we have 52 choose 5 is equal to 52 factorial all over the quantity of 52 minus 5 factorial times 5 factorial. And 52 minus 5 is 47. So now we have 52 factorial all over 47 factorial times 5 factorial. Let's put that into the handy dandy calculator because nobody has time to simplify that. And our result is 2,598,960 different hands. That is example 2A. Let's move on to 2B. How many full houses are possible? Remember, a full house is 3 of one kind and 2 of another kind. One hand could be the 2 of hearts, 2 of spades, 2 of diamonds, ace of spades, and the ace of clubs. Or we could have the ace of clubs, 2 of hearts, 2 of spades, 2 of diamonds, and the ace of spades. Or we could have the ace of spades, ace of clubs, 2 of hearts, 2 of spades, and the 2 of diamonds. What do we notice about each of these hands? That is correct. The three different hands are actually the same, so order does not matter. That means we're going to use combination to find our answer. So N is the amount of each number or letter, so 4, and R is the amount we want. Let's continue with these examples, 3 2s and 2 aces. So to find the different combinations we could have with 3 2s, we do 4 choose 3, and using the formula we have 4 choose 3 is equal to 4 factorial all over the quantity of 4 minus 3 factorial times 3 factorial, and 4 minus 3 is 1 factorial. So now we have 4 factorial all over 1 factorial times 3 factorial. Let's use the calculator, or we could simplify, and the result is 4. Now, we have to do that with the aces. What do we think we're going to put into the combination? That is correct, 4 choose 2. So now we have 4 choose 2 is equal to 4 factorial all over the quantity of 4 minus 2 factorial times 2 factorial, and 4 minus 2 is 2. So now we have 4 factorial all over 2 factorial times 2 factorial. Let's use the calculator, or we could simplify, and our result is 6. We have one more obstacle here. Do we know what it is? That is correct. We could have 2 2s and 3 aces. So there are 13 in each suit, which is our N. And we have 2 ways, which are 3 2s and 2 aces, or 2 2s and 3 aces. So that means we have 13 permutations of 2. And that is equal to 13 factorial all over the quantity of 13 minus 2 factorial. And 13 minus 2 is 11. So now we have 13 factorial all over 11 factorial. Let's put that into the calculator, or we could simplify, and our result is 156. Since everything is happening simultaneously, we have to multiply our results. So we have 4 choose 3 times 4 choose 2 times 13 permutations of 2. This could be our answer without a calculator, but since we have one, let's go ahead and find it, and our result is 3,744. Or we could use the results that we already found, and 4 times 6 times 156 is also equal to 3,744. That is example 2B. Now it is your turn, so go ahead and pause the video here so you can take your time to answer this question, and I will show you the result in 3, 2, and 1. Did you get it correct? Superb. If not, there's always tomorrow.